Good morning. Today I'm here to talk about our research on fine-grained few-shot image classification with a bi-directional reconstruction method. I'm Wang Yuanrun and I'm joined by my teammates Wang Yanxiang, Geng Yi, and Ding Yiting. Let's start by understanding the problem we want to solve. Fine-grained few-shot learning is about telling apart very similar things, like different bird species or car models, when we don't have a lot of data. Our main goals are to make differences between classes bigger and make differences within the same class smaller. We do this by using a bi-directional reconstruction framework and a mutual information model to pick out the most important features. Our researchers have tried different methods. For example, they used local cross-reconstruction, built feature optimization networks, and they create an attention model. We tested our method on 3 datasets: CUB dataset, Stanford dogs dataset, and the Stanford cars dataset. These datasets are hard because the differences between classes are small, but the variations within each class are big. Our framework has 5 main parts. The first is feature extraction. We use ResNet 12 with job block to reduce overfitting. Job block helps the model learn better by randomly dropping blocks of features. The job block formula is shown in the figure. This formula helps adjust how many features are adopted to prevent the model from memorizing the data. The second model is the AMA selection model. This part finds the most important local regions by calculating mutual information between global and local features. We use KNN to estimate entropy and add noise to make it more robust. To be specific, we find the best local regions by maximizing mutual information. Noise injection makes sure the model won't tricked by unimportant details. The third part is feature self-reconstruction model. We use transformer self-attention with positional encoding. FSMR makes features within the same class more consistent by focusing on the important spatial areas. The positional encoding formula is shown in the figure. This helps the model understand where features are located in this image. The next model is a feature mutual reconstruction. This part rebuilds feature between support and query samples in both directions to make differences between classes bigger. The last is classification model. We use cosine similarity to predict labels based on the refined features. The next part is experimental results and analysis. Our method works better than others. On CUB dataset, we got 86% in one shot and 95% in 5 shots. On dog dataset, we achieved 78% in one shot and 89% in 5 shots. On cars dataset, we got 91% in one shot and 97% in 5 shots. In ablation study, using trunked cross entropy helped a lot. On dogs dataset, it increased accuracy by 1.8% in one shot and 1.4% in 5 shots, showing it makes few-shot learning more stable. In conclusion, our bi-directional reconstruction framework with AMA selection does very well on fine-grained few-shot tasks. It's lightweight and can be used in areas like biometrics and medical imaging. In future work, we plan to test our method on more datasets, like medical images, and combine trunked cross-interface with other optimization methods to make the model even better. These are the papers we refer to. Thank you for listening.